So yeah, thank you for the invitation and for what looks to be a very exciting workshop. Today, I'll be talking a little bit about applications of some areas of math that maybe don't come up as much when you read the introductory machine learning or data science textbooks, but I think hold a lot of promise. And my main thing to get across will actually be more of the breadth of what people are out there doing rather than, very specific technical details about it. So hopefully it's an enjoyable talk to watch. And I'm happy to point towards specific works if you're interested in really digging into the details. So deep learning has advanced machine learning across a range of tasks. We all see this, whether we actually work in the field or just read the popular press, we see this everywhere. From the visual arts with some of the new generative models that have been released, like Stable Diffusion, I think is the most recent one, to what's perhaps more interesting which is some of the science applications like AlphaFold and things like that. But of course, not to oversell things, there's still a lot of serious challenges here. So the current machine learning methods in general are easily fooled by spurious correlations in the data. There's adversarial examples that can fool them. They take in all the biases that are present in internet data and a host of other things that are maybe not so desirable. So there's a lot of work to do. And one of the things that I'm hoping to get across is that there's definitely a role for mathematicians in all of this. It's just a matter of us finding the right problems to work on. So I'm going to break this into two parts. I had algebra and topology in the title, and I'm going to break it up that way. So in the first part, I'll talk a little bit about data, symmetry, and deep learning. I noticed this morning that there's another speaker who will talk about a similar topic. I will keep it fairly surface level, and I'll let him dig into some of the details, but hopefully give you a taste of what's out there and highlight a little work that my group has done in this area. In the second part, I will talk about the influence of topology beyond TDA. So topological data analysis is definitely the most maybe well-represented aspect or influence of topology in data science. But there's a lot of really interesting work that uses structures that arise from topology or inspired from topology to inform things like network design and such. So I'll talk a little about that as well. So my high-level takeaways, and I'll flash these again at the very end of the talk. These are just some lessons that we've sort of learned in trying to apply these subjects to mostly deep learning. So the first is that when you take some idea from math and try to apply it to deep learning, you really should take the very bare minimum possible, like take the kernel of the idea and see if you can get that to work before you start importing a whole lot of extra structure. The math should not replace the learning, it should limit or constrain it. And I think actually pure mathematicians are in a great position to do this, because we're sort of taught how to look for larger general structures without, and very much able to ignore like the engineering details that sometimes I see other folks get bogged down in. And finally, then, when in doubt, math definitions are meant to be broken. So go with what makes the learning possible, what solves the task, what advances the science. And sometimes along the way, you'll come up with new structures or variants of existing structures that are interesting in their own right. Okay, so I roughly broke up the interaction of math and deep learning as I see it into two parts. This morning, as I was watching another talk, I realized there's a third one, which I'll mention, but we'll start with these two. So the first is there's a lot of people doing really interesting and important work on how does deep learning work. So they take mathematics, mathematical tools, methods, and try to answer questions about why highly overparameterized models learn, how that's different than classical machine learning, deep double descent, lost landscapes, etc. Very important and very interesting. It's not what I'll talk about today. What I'll be talking about today instead is maybe slightly less common, and that is how pure mathematics, ideas from pure mathematics can be leveraged to build better models. So this can range from like, how do I incorporate natural symmetries into my machine learning model, to leveraging topological features and structures, learning on manifolds, which I won't talk about. I think a lot of the incorporation of domain knowledge in physics and things like that uses some interesting ideas from math, which I also won't talk about, but it's definitely out there. And then the third one I realized this morning is people who are applying machine learning to solve math problems, which is actually, I think, one of the most exciting areas, but won't say too much of it in this talk. It sounds like there are, or have been, and will be some more speakers that'll discuss that. So the first point I want to make, which I think it's a really obvious point when you think about it, I think it's underappreciated. It's easy to forget, let me put it that way, is that deep learning is all about composition. So you're taking a bunch of really simple parts, simple types of functions that we understand well, and composing them in potentially complex ways to enable pattern fitting at a much larger scale. And I think this really fits well with how the tools and ways of thinking that pure mathematicians already have, a la category theory, where we think a lot about things in terms of composition, and generally, I think, much more comfortable with it than maybe other disciplines are. So there's already some connections there. And just to kind of give one rather stupid example of this, I was thinking about recently, in pure math, we define a lot of things by, say, commutative diagrams, at least in certain areas of pure math. And the folks in deep learning are also using diagrams. They're not really thinking about them in terms of commutativity, I don't think, most of the time. But they're also composing things and looking at how all these pieces fit together. I was curious whether you could go from a definition that maybe is framed in terms of a commutative diagram to actually a learning goal. And so what I did was I took the very simplest thing you can do, which is define an identity element via a commutative diagram. This is just the usual definition for the identity morphism, and see if I could learn the identity from that. So what I did here was I translated this commutative diagram into a very simple loss function. You have to, of course, make some choices here, but indeed you can learn going from this random matrix with all the colors, which represent the size of the values, to the identity matrix, just going from this commutative diagram. So that's kind of a stupid example, but I think it gets the point across that there's ways to connect these things that maybe haven't been done before. And my question, which I don't have an answer to, is, are there categorical structures that are not obvious? I mean, I know how to make the identity matrix. I didn't really need to learn that. Maybe there's things that I don't know. Maybe there's things that have to be learned that are defined in a more abstract way like this, that it would be useful to explore. I don't know, but I think it's kind of interesting to speculate. Okay, so let me launch into my first part. So I'll talk a little bit about symmetry. Symmetry, of course, is everywhere in the real world. I work mostly, these days at least, in computer vision, so a lot of my examples will be pictures. They're nice to show in a presentation, but of course there are other data types with other symmetries out there. So you and I would look at these pictures of this dog, and we hopefully be able to identify both of them are a dog, and maybe even the same dog. There's no reason to think that a neural network that is trained on pictures of upright dogs would necessarily get the upside down dog. It might, if it had seen enough examples of upside down dogs, but it might not. If I were to show you a new animal and then show an upside down version of it, you probably wouldn't need to see a bunch of other examples of upside down versions in order to realize that, hey, this is just the thing I've already seen, but it's upside down. So these models don't have invariances built into them, and that can be a big problem. People may have seen this example. I don't really know where it came from, but anyway, there's some vision recognition system, hopefully not on a self-driving car, that was not able to recognize an upside-down car because that had crashed because it had never seen upside-down cars. So this is something of concern, especially when these systems start to be deployed in the real world. So there's two ways that people try to make these models invariant to symmetries. The first is through something called data augmentation, and this is kind of the simplest thing you can imagine doing. Just if you want the model to learn how to recognize upside down animals, you show it upside down pictures. This works great when when the transformation is something like rotation that I can just do to any image. It becomes much harder when I don't have a way of simulating the transformation. And that's, I think, largely an unsolved problem, how to deal with that, other than collecting more real data. The other method of doing this is to use something called equivariant architectures. This is, except for one critical example I'll talk about later, which everyone knows, this is not as well known, but certainly something that's gaining in a lot of popularity in the community. So the basic idea here is you constrain each of your layers, and remember you have many layers in the network, to be equivariant to the symmetries you care about. And then either, depending on how you structure your network, either you get equivariance for the whole thing because the composition of equivariant functions are equivariant, or you play some games with data reduction so that you actually get invariance from progressive equivariance. So that's great. And of course, you can frame this stuff in terms of commutative diagrams as well if you want. We can think about some symmetries for images, for example. There's translation invariance. You probably, if you only show a model pictures of dogs on one side of the image, it'd be great if it could recognize that dogs are still dogs, even when they're on the other side of the image. Rotation, we've already talked about. Scale invariance, invariance to color shifts, things like that. And of course, the important thing to remember is all of this really depends on the problem you're trying to solve. So you really have to go back to what is the task that needs to be handled. So for translation invariance, of course, that's not true for plots or charts, which people certainly try to learn off. Rotation invariance, not true if you're doing, say, MNIST and you have 6s and 9s. Scale and color invariance to color shifts are often not something you actually want in certain science applications and others. So we can start to break this down and think about this a little more mathematically. So I have some group. It's not all of these invariances correspond to a group, but that's the case we'll cover today. And I have a model F that takes input in X and gives output in Y. A group acts on both these input and output spaces. Maybe that action is trivial on Y if you want invariance. And you would want to ask certain things about this function. So is this an equivariant function? Blah, blah, blah. So the problem, so if F was linear, then there's a lot of things that we could say, of course. When F is a really complicated, highly overparameterized function that we don't understand in many ways beyond just this, it becomes problematic to even check invariance or equivariance, depending on what you care about. So fortunately, of course, these models are frequently just always the composition of simpler functions. And then what you can start doing, you say, maybe I can't get a handle on invariance, equivariance for the whole thing. But what I can do is I can look at each individual part and ask what I can do there. So if Fi in this case is a linear map, then of course we can say a whole lot more about what it means to be equivariant and so forth. And of course, there's other components of this. There's nonlinearities and other layer types. But it turns out that a lot of times those are very simple and they can be handled as long as you can deal with the linear layers. So here's an example of a network that is not equivariant, is not not a rotation equivariant architecture, and we can look at what data looks like as it passes through this network. So the way this network is structured, it has a bunch of convolutional layers, and it ends in an affine transformation. And what you can see is sort of visually displayed. This network works like many convolutional neural networks. What it does is it takes in 3 channels that have some spatial dimensions, so a red, blue, and a green. This is MNIST, so okay, it doesn't actually have those, but I faked it. And what it does is progressively, as it runs convolutions over these, it reduces the spatial dimensions and increases the number of channels. So you have a 3 tensor every time, but you're growing channels, reducing spatial, until at the very end you have just a vector. And what it turns out is that if all these convolutions are equivariant to some specific symmetries, by the end what you should get is invariance, because you shrunk the spatial dimensions that are being acted on. And this is kind of the idea behind a lot of these equivariant architectures. This network is not equivariant to rotation, and we can sort of see that if we look at these images. So if this was truly equivariant and every layer, all these hidden layers were equivariant as well, what we'd expect is as I rotate this 2 and put it in the network, it would just look like it's the same image, but it's rotated. And we can see that for this first hidden layer, it actually looks reasonable. You can see some of it's changing as it rotates. It's a little worse for the next one. And by this layer here, you can kind of tell there's some sort of rotation in the background maybe going on, but there's quite a bit of change. And what this change is indicating is that this thing is failing to be equivariant. So I should note this model in theory has learned invariance to rotation. It was trained on a data set that had digits at all different orientations. It did quite well. So the invariance in this learned version is learned somewhere else. And I don't know where that is. It's an interesting question to ask. What this network is, though, is invariant or equivariant to translation. And hopefully this looks more, this is apparent when you actually look at these. So here where I'm translating this first one really does look like I'm just taking this image of this hidden representation of the 2 and just translating it along the screen. This one also, I think, looks pretty good. You get some edge effects that happen. And even here, where in the other example, we really were not seeing much structure at all. Here, yes, you have edge effects, you have interpolation effects, but I think it looks pretty good overall. And that makes sense since each of these layers was designed to be translation equivariant, and it ends up being approximately so for the reasons I stated. So that's great. And, you can take your favorite group and you can play this game of trying to find the right constraints on your matrix so that only equivariant layers are learned. And of course, since we're dealing with linear things, if we don't have a bias, then we can do all sorts of fun things like decompose into irreducibles and get block diagonals and ask what the irreducibles that are most important are, and all this sort of thing. And of course, in the machine learning community, people love this because the structural theorems that come with group representations mean that they can have fewer weights and have faster learning and things like that. And I'll show an example of this in a minute. So a lot of the work, the basic work, I think, or first pass work at this has been done. I think there's actually a lot more to do here that mathematicians can contribute. And I'll talk about some of those open questions at the end of this section. So you can ask, like, what have people done about in this space? What do people care about? So there's a lot of examples. This slide certainly doesn't cover all of them, but a few of the ones that stand out. So Imagery, which I already showed, is of course a big thing. This is really, I think this is where all this started, was people wanting things like rotation, equivariant networks for things like microscopy, where orientation doesn't matter, or satellite images, certain types of medical images. Of course, when you get into 3D, then you start dealing with things like molecular structure, point cloud, LiDAR point cloud data for self-driving cars, certain types of graphs and things like that. And then there's another side of this that's over in the symmetric group. So there's certain data types where order doesn't matter, and yet you need to use some order when you enter the data into the network. So generally what you would do is if you have a set, you need to choose some order, you put it into a vector and add it in, but you really don't want the model using any information about the way you've chosen to order that, since it's arbitrary. And so people look at symmetric group equivariant things for both sets and graph nodes, and a number of other types of problems. There's some more exotic groups I think folks use who apply deep learning to physics, but I don't know enough to say too much about that. Okay, so I'll talk a little bit about some of the stuff that our group has done in this space. And I'll focus on some recent work which asks some questions about, like, first of all, how do we measure what is going on here? Because a lot of people are coming up with a lot of approaches to building in invariance, and there doesn't seem to be a systematic metric to actually empirically measure invariance in functions that you can't check it like you would a linear map. And then some further questions such as, for a lot of people, they would say, I'd rather not build, if given the choice between these sort of complicated equivariant architectures that hard code equivariance into my network, or just training with augmentation, just getting a little bit of extra data, I'd rather do the extra data thing since it's easier to program. We speculated that actually this would be very bad for deployment situations where you might be seeing new data for which you didn't learn invariances. If you're depending on learning, you better hope that the invariances you learn are generalized. So we looked at that as well. So first, let me say a little bit about this metric. I won't say too much. This metric turns out to be kind of what you would expect it to be. We're basically looking at how much a function fails to satisfy the standard equivariance equation. There's a few subtleties here. Probably won't get into most of them. What I would highlight is that it really depends. This metric really depends on what your notion of distance is in the output space. So we looked at equivariance in terms of hidden layers of networks where you had, for example, you're comparing 3 tensors. We also looked at hidden layers where you're comparing vectors. We also looked at probability distribution outputs. Each of those is sort of its own thing, and you need to come up with a metric that makes sense in that case. The other thing to point out is that in machine learning, people might not care if their function is equivariant on all possible inputs. I may not care that my function fails to be equivariant when I enter random noise. That's not something I'm expecting to encounter in my problem. So there's this notion of like local equivariance. I only care about being equivariant on some data distribution. And it's interesting to think about that, how that might interact with the mathematics. Oops. Okay. Yes, so I will not say too much more about that. So in the experiments I'll show in a second, this is the basic outline. So we'd like to understand the equivariance of examples from a data distribution. I'm going to look at it in 3 places. I'm going to look at it in between convolutional blocks. So if you remember here, I have some 3 tensors that basically correspond to maybe slightly reduced spatial dimension, and then many channels storing data about that. I will also look at it in the latent space of the model, which just corresponds. This is the final final extracted feature layer of the model where I've sort of done all my nonlinear things, and I'm ready to just do some hyperplane separation of my data. And then finally, I will look at softmax probabilities, or these are just the probability that a given example belongs to some number of classes. So this is just a finite probability distribution. So I will say a little bit about that, but first let me show you some nice pictures. So just to sort of validate that you actually are capturing some structure here, you'll notice that when I take a 4 and I start to rotate it around, so these are actually two 4s, one with a red border and one with a blue, I actually do get loops in my latent space, which is my feature extracted space. So these images actually correspond to vector 64 length vectors. I, of course, had to apply some dimensionality reduction to visualize it, so you've lost a lot of information, but it's a nice picture. And it shows, for example, or suggests that these models actually group the digits, different parts of different orbits together. So rather, if these were truly invariant, you would expect the orbits to be separate. In fact, that doesn't seem to be the case. The model has seemed to learn different rotations or the same rotation of different digits together, and which is definitely not invariance. Just to show another pretty picture, this is for a model that had a latent space of 512 dimensions, and this is just an orbit of a single digit as it's rotated, and you can see these things get pretty complicated. Seems to be quite a tangled mess of the point as it moves around in this high dimensional space. Okay, so the first question we ask, are equivariant networks actually more equivariant / invariant? And how is that invariance learned, if we can say anything about it? The answer that we came up with is that, and I should show which part's which, is that the equivariant networks are more consistently equivariant. In this case, equivariant is orange. It is actually C8 equivariance for the cyclic group or rotation group of order 8. And you can see that in all cases where invariance represents being smaller values, you get more invariance for these models than you do for a CNN who's just learned its invariance. The interesting thing, I think, is that what you see here is that neither model is actually learning any, well, the C8 CNN is not learning any additional equivariance in its convolutional layers, which correspond to the left plot. And the CNN is not learning really any at all, except for some small drop at the beginning. So it's somehow learning to be invariant in a way that's very different than our hard-coded method, and it would be interesting to understand that. It seems that the learned invariance sort of catches up at the end a little bit, but if you really care about invariance, you should use the equivariant architectures to achieve this. We also looked at outed distribution. So I told you before, these are trained on MNIST images, which are images of a bunch of digits. And you can see here that we got a lot of different versions of this. So either we corrupted the image itself, or we chose some other data set that were maybe similar to digit images, maybe not in the case of CFAR, and look to see, like, did the learn invariance generalize out of that distribution? Again, here lower values are better, and what we see is that in general the C8 CNN did better. The one sort of funny thing to note is that for the output of the model itself, actually the most invariant one was the one with random weights that did terribly. So it's important to keep in mind that invariance is sort of a secondary benefit and probably not the thing to optimize for a network with zero weights that gave a constant value is very invariant, but probably not something you want. Okay, so let me wrap up this section by leaving a few questions that are, to my knowledge, open in this field. So this equivariant architecture. So first of all, for the equivariant architectures, there are people who have smart people who have found ways of constraining learning at linear layers so that symmetries are satisfied, equivariance is satisfied. I suspect that there are other ways of doing this, and it would be interesting to get experts, maybe from representation theory or related fields, to look at this problem and see if there's other approaches that would be worth exploring. There's certainly a difference between being able to say that we have constrained learning to be equivariant, and we've constrained learning to be equivariant in a way that works well. And that often is an empirical question that you need to run experiments to identify, but something that's definitely worth doing. As I've mentioned a few times, it would be interesting to learn, if you're just learning invariances, it would be really interesting to learn how that is actually happening naturally, and how different that is from our sort of hand accomplished approaches. And then finally, there's a lot of groups that have not been, no one has studied this for, mostly because there's not an application for them. But I suspect that given that mathematicians are interested in these tools now, there's some more interesting and complicated groups that will appear for which one might want an equivariant architecture. There's problems where the group action is not linear, such as like color things, or not obviously linear. And finally, there's this issue of where everything we've done is symmetries to really the data type. So in this bottom picture of the bananas, I talked about rotation a lot. Rotation is something you can do to any image. It's really something you're doing to the data type. There are, of course, other symmetries that are symmetries of the content of the images. So here I've taken this banana and I've rotated it in three-dimensional space. So that's not an action on the data type. If I gave you another picture of, say, a dog, you wouldn't be able to rotate that dog in the image without going and collecting more data. These types of symmetries would be really great to be able to handle. And at this point, there's certainly some approaches to this, but I think there's a lot more work that could be done. It's a hard problem. Okay, so
Can I ask you a question?
Yeah,
Yes.
there's another question in the comments also, but Kvinge, if that's you go ahead.
Yeah. How can you make activation equivariant? So here, are you considering activation process?
Yeah, so the way that folks usually do this, so it actually depends on the representation you're using. So for example, with the if you're using the regular representation for a finite group, then what you can do is it turns out that a lot of the activations that people already use work. If you want to decompose and use like irreducibles, for example, you have to do a little thinking about how to make those so that they preserve equivariance as you go from layer to layer. I've seen a number of examples of it. I also suspect that some of the cases where equivariant architectures lag behind some others, it might be due to these in the fact that you have to change the nonlinearities, and maybe the new nonlinearities are not optimal, but I don't know for sure. So one thing maybe to say along those lines was there's a few works that look at what happens when you take your representations that are living in the hidden spaces, and you choose them to be different things. Like, what if you only allow certain irreducibles? And disappointingly, at least to me, it seemed to be that using the regular representation for the groups that these folks were looking at seemed to always be the best. It would have been very interesting if certain irreducibles were better at carrying information than others, but I haven't seen much evidence of that. But like I said, that could be because you have to make some architectural adjustments to the nonlinearities if you do choose to make use specific irreducibles rather than the whole regular representation.
Yes, so I said I monitor the chat for you, and Avash, I think the name is, has written, is this model based on group or steerable CNNs? I have to admit, I don't understand that question. So if Avash wants to unmute and...
Yeah, so most of the stuff I showed here was based on steerable. I sort of swept the distinction under the rug, but yeah. All the experiments were based on steerable. In fact, I should have cited, this is the E2 generalized steerable E2 CNN paper.
Yeah,
a really nice work.
Thank you very much.
Cool. Any other questions before I go on to my next section? Okay. All right. So in the next section, I'll talk a little bit about the influence of topology in deep learning. And what I'll do is I'll take three structures that I think are sort of, well, to folks that work in these fields, very sort of elementary, basic things. Certainly maybe not felt that way outside of those fields, but I'll talk a little bit briefly about some examples of how sheaves and simplicial complexes are being used in deep learning, and then I'll spend the rest of the time talking about some of our recent work on fiber bundles as inspiration to deep learning architectures. And my bold claim in all of this is that deep learning and machine learning in general has reached a level of scale and abstraction where we really should be going to look in places for some of these really fundamental notions, a lot of which I think mathematicians have discovered for independent means that capture sort of very basic structures that would probably be of great use if you're someone who goes around composing lots of things together as deep learning people do. Okay, so the first one, and again, I'll talk about these rather quickly. This is not my work, but I think it's worth highlighting just to give a sense of the breadth of what people are doing. So this is sheaves for learning on graphs. So of course, I think since we have mostly math, or at least some mathematicians here, sheaves are a very common tool in several disciplines of math. You can think of them, if you don't know much about them, you think of them as a way of principled way of tracking data on some spaces. When they're applied to graphs, I guess they're called cellular sheaves, can capture relationships between nodes. This is in contrast to if you just took a graph as it is, where you have the only real information is whether two nodes are connected or not. And so some topologists took this idea and sort of melded it together to create graph convolutional neural networks, so a type of neural network built for learning data on graphs, and used the sheaf framework to be able to incorporate information about the relationships between nodes and how data passes between them, which I think is a great example of how you can make these things more domain aware, because there's a lot of extra information in graphs that isn't often included in just the bare bones graph itself. Yeah, so this is from a paper called Sheaf Neural Networks by Hansen and Gebhardt, and I think there's been some amount of follow-up work on this as well. So for simplicial complexes, so there's a few applications actually of this. My understanding is that UMAP, the popular visualization tool, uses some ideas at least related to simplicial complexes. That is something interesting maybe to look into. I'll talk today about one of our work from a year ago that was looking at how to use simplicial complexes to imbue small sets of data with enough structure to learn from. So for just to set the bar, simplicial complex, a way of building higher dimensional structure out of a lot of simple building blocks, namely simplices, and it tells you how you are allowed to glue them together. It's useful when you're modeling spaces. So what we encountered was we were dealing with a problem where we had very little data for the task we were doing. So maybe we had a neural network that had been trained on a lot of different things, but it had never seen some new classes. So suppose maybe one has only 5 examples of some particular species or something like that. How do you learn on that? So the obvious first thing you could try to do is say, well, I don't have much data, but I'm going to train my network anyway. And what you'll find is your network will very much overfit for those 5 examples you have. So what we did instead was we used the network that was already existing to extract maybe useful features that captured something salient about that class, and then within the latent space built simplicial complexes, well, some generalization of simplicial complexes that could capture the structure that and interrelationships between those specific examples without overfitting to them. So it turned out this worked very well and beat the state of the art in several types of problems. So we were quite excited about this. And I do think that the regime where you don't have much data and you really have to be clever about how you're doing things is an opportunity for mathematicians, since you can't really just play the take more data, throw more data at the problem and hope things get better, which oftentimes is unfortunately what works best in other situations. So the last thing I'll talk about is a problem in material science that we just published a paper on this spring in iClear. So the background to this is advanced manufacturing is the process of generating materials at regimes that are not usually encountered. It holds a lot of promise to current problems in the world, since it's able to generate materials which are stronger, lighter, more durable via processes that are more energy efficient, which of course is something we definitely need to be doing. The unfortunate thing is that these manufacturing processes are sort of the Wild West in terms of understanding what's going on. Oftentimes, because of the regimes they operate at, the physics models are not quite there yet. And so when the material scientists go to run experiments, they're largely operating on intuition and trial and error. So the problem then is you have this manufacturing process. It takes input material over here and puts output material over here. You're hoping that when the output material has some new amazing property, it's much stronger, lighter, etc. And in order to achieve that, the material scientist has to choose a bunch of what they call process parameters. So these might be the temperature that the material experiences during manufacturing, maybe the pressure, maybe the rotation rate, etc. And so when you first look at this problem, at least as a machine learning person, you think, well, this is kind of fits into one of my standard templates. What I'm going to do is I'm going to build you a model that you tell me what the temperature, pressure, and rotation rate, etc. are, and I'm going to predict the properties. And then you don't have to spend hundreds or thousands of dollars to run individual experiments. You can just try to experiment with your this model, which costs very little running on a GPU, and you'll save a lot of money. What was interesting was that when we spoke with the scientists here, what we learned was that this was good, but it was not really what they wanted. What they really wanted to be able to do was to be able to specify a property over here and have us produce all the different combinations of temperature, pressure, and rotation rate, for example, that would achieve that property. And so this doesn't fall exactly into a template in machine learning. If you're thinking of this as a function, this is sort of like asking about the fiber for some individual element in the output space. So just to make this, maybe put this all in pictures, and also have the obligatory dog and cat picture in the presentation. The traditional thing that we were expecting to do was, you hand us a picture of a dog and we give you the label. What they actually wanted us to do was they specify the label and we give them all different pictures of dogs, so to speak, which is obviously a much harder problem. And while there are sort of approaches that sort of fit this direction, there was nothing that exactly fit what we wanted to do, which was actually a regression problem. Not sure why that arrow went up. So the way that we thought about this was in terms of a disentangling problem. So you have this big cloud. If in this case, we'll talk about the picture since it's maybe a little easier to visualize, but for us, it was the process parameters. You have this big cloud of data, and you'd like to disentangle it so that you can distinguish between the variation related to the task, which in this particular cartoon example is the species of animal here, and the variation that's independent of the task. So orientation, lighting, background, all that sort of thing. And one might think that maybe you can just do this at a global level. So I'm going to disentangle the entire space into a product of these things somehow. We ran some initial tests, and also just intuition said that this was probably too much to ask, that this was actually a product space. And so the next thing we started to wonder is that, maybe locally we can do this disentangling. So of course, this made us think of fiber bundles, where kind of the underlying idea is that locally you can these things are homeomorphic to some product space that has a neighborhood of your base space, and some fiber, which is constant around the whole space as a whole, but maybe you can't globally find such a homeomorphism. So I won't go too much actually into the definition of this, other than to just quickly run through and just remind you some of the parts that one would need to do this. So first of all, you need some sort of surjection from your total space to your base space. You also have a certain commutative diagram that you need to be satisfied, which basically says that the way that you decompose individual neighborhoods, or the inverse image of neighborhoods in this total space, agrees sort of with your projection map in the right way. What I'll instead talk about is what this looks like in terms of the data. So when we went from this kind of standard toy example, geometric or topological picture, and tried to think about what this means in terms of data, what we found was what the translation would be, at least for this cartoon problem, is that, say I take some neighborhood in my output space, which is now serving the role as the base space. I need a way to then decompose the inverse image of that. So if my neighborhood is just around dogs and cats, I'm going to need to decompose all the images of dogs and cats into a product that has the labels as one part of the direct product, and then some sort of notion of fiber that captures the variation in those different classes. And we, of course, are not interested in classification, but it's an easier picture to draw. So this process of taking these kinds of abstract structures and doing some sort of deep learningification of them is interesting. I find it actually to be kind of fun. But basically what we did here was, okay, you have many local trivializations. How do you encode that in the network? Well, we just added a conditioning vector. So some extra piece of data that came in with the input that informed the network. Okay, I'm in neighborhood I, and now I need to change my weights accordingly to be some different function. We utilized invertible neural networks, which are a family of neural networks or neural network parts that give actually an invertible function, which is very cool. If you play around with these things and haven't played around with invertible neural networks, highly recommend it. They're very interesting, I think, especially to mathematicians. And then finally, we needed to choose a fiber. So in the process of learning, you have to make some assumption about what this fiber looks like. And so you have to make some assumption about the distribution you're expecting of variance that is not task related. So that might be quite hard for these images. We were using something much lower dimensional, this material science data, which it turned out to be not so bad. We experimented with a number of distributions, some of which worked better than others, and I can say more about that later if people are interested. So this is just a picture of the architecture that we ended up using. Let me just say that so once you've trained this thing, why is this useful to material scientists? Because then what we can do is they can specify their Y value. Maybe this is strength, maybe this is lightness, maybe this is something else that they care about. You can sample from some distribution that captures the variance of all the different process parameters that yield that strength, and put this back through the network. And what you'll get is a continuous, well, as many as you want sampled examples that have that property, at least according to what the network has actually learned. We tried this on some toy examples that were fiber bundles. BundleNet, which is the name of our model here on the left. You can see it reconstructs the torus and the Mobius band quite nicely. These other models that we tried that weren't exactly designed to do this thing, but one might speculate could, didn't do so well, as you can see from the reconstructions. We, since this graphic was created, tested some model called conditional normalizing flow, did a bit better. So there are things that are better than these three that we pictured here. And the final thing that one might wonder is in all of this. So firstly, is the data actually a fiber bundle? I think almost certainly not. But it's a useful construction for modeling this and designing a network. Secondly, and maybe more specifically, we have this assumption that all fibers are the same in our network, and it's unclear whether this is actually a good thing to assume. We tried a number of examples, including some real data that I'm not going to picture here, and found that, at least on the lower dimensional stuff, having fibers that actually differed in their structure throughout the space or throughout the data problem didn't really seem to matter. This example was a pinched torus where some of the fibers in the torus are actually a circle and some of them are just an interval. And the BundleNet does okay. It certainly does a lot better than these other models where it not even clear that they are the shape that they're supposed to be. Okay, so I have 5 minutes left, so I'll reiterate my takeaways and then end. So pure math, I think, has a lot to offer deep learning, not only in analyzing what exists, but developing what comes next. I picked a few avenues here. There's a lot more. The lessons we've learned is that you should always import sort of the least possible. Take maybe inspiration from the math, but not be constrained to the math. Develop structures that are capable of sort of channeling learning in certain directions rather than replacing learning with some hard-coded choices. And of course, when in doubt, go with what solves the task. Don't be controlled by the definitions, which are in some sense meant to be broken. Okay, thank you.